Picture a time when the universe was nothing but a sea of darkness, an endless, silent ocean of neutral hydrogen gas. No stars, no galaxies, not even a whisper of light. Just emptiness stretching across the cosmos for millions of years. But then something profound happened. A flicker emerged. A glow began to spread. Slowly, gently, light pierced the shadows, igniting the vast cosmic expanse until it shimmered with the birth of the first stars and galaxies. This shift from complete darkness to brilliant illumination marks one of the most dramatic transformations in the history of our universe, and it's known as the Cosmic Reionization Era. It's a chapter so mysterious, so full of unanswered questions, that it stands as one of astronomy's greatest and most compelling puzzles. What caused this incredible transition? How did the first sources of light stars, galaxies, even black holes flood the cosmos with enough energy to tear atoms apart and turn an opaque universe into the transparent, star-filled wonder we gaze upon today? These aren't just scientific questions, they're deeply human ones. They connect us to the very origins of everything we see when we look up at the night sky. The Cosmic Reionization Era holds secrets about how structure formed, how matter organized itself, and how the conditions for life as we know it began to emerge. It's a story written in light, radiation, and time, a story we're only just beginning to read. In this video, we're going to explore 25 mysteries that make this era so captivating and elusive. From the nature of the very first stars to the role of supermassive black holes, from the distribution of ancient hydrogen to the faint echoes of radiation we can still detect today, each mystery pulls us deeper into understanding not just how our universe changed, but why it matters to us now. This journey isn't just for scientists, it's for anyone who's ever looked up at the stars and wondered how it all began. So let's step into the darkness together and watch as the cosmos lights up for the very first time. Our journey into the cosmic dawn begins with the architects of light themselves, a generation of stars so ancient and powerful that they fundamentally reshaped the universe. These weren't just the first stars, they were titans born from a cosmos that had never known starlight. We call them population 3 stars, and their existence is one of the most critical, yet entirely theoretical, pillars of our understanding of the reionization era. Unlike the stars we see today, which are enriched with heavy elements from previous generations, these pioneers formed from a perfectly pure, pristine soup of only hydrogen and helium, the raw elements forged in the Big Bang itself. This lack of heavier elements meant they could collapse into truly monstrous sizes, with many thought to be hundreds of times more massive than our own sun. Imagine the sheer power contained within such a behemoth. Its surface would blaze with a ferocious intensity, emitting torrents of high-energy ultraviolet radiation. This radiation is the key that began unlocking the entire reionization process. As it streamed out into the surrounding darkness, it slammed into the vast, cold clouds of neutral hydrogen gas that filled the early universe. Each photon of this extreme UV light carried enough energy to violently strip an electron from a hydrogen atom, transforming it from a neutral, light-absorbing particle into a free-floating, positively charged proton and a free electron. This process, ionization, is what began to clear the cosmic fog, creating ever-expanding bubbles of transparent, ionized plasma around these first brilliant stars. They were the universe's first lanterns, pushing back the darkness inch by inch. Yet, for all their monumental importance, we have never directly seen a single population 3 star, and the reason for their elusiveness lies in their very nature. Their incredible mass was both their strength and their ultimate downfall. They lived fast and died young, burning through their colossal fuel reserves in just a few million years, a mere blink in cosmic time compared to the billions of years our sun will shine. Their deaths were just as spectacular as their lives, ending in cataclysmic explosions known as hypernova, far more energetic than any supernova we observe in the modern universe. These violent events not only seeded the cosmos with the first heavy elements, but also completely obliterated the stars themselves, leaving no direct fossils behind for us to find. This presents an immense challenge for astronomers. How do you find something that vanished almost as quickly as it appeared over 13 billion years ago? We believe they formed not in grand galaxies like today, but in relative isolation or very small groups within the darkest, densest pockets of the early universe. Our most powerful telescopes, like the James Webb Space Telescope, are now peering back to these extreme distances, not to find the stars themselves, but to hunt for the unique chemical fingerprints they would have left behind in the atmospheres of later generation stars, or the telltale signs of their ferocious radiation imprinted on the ancient gas between galaxies. The hunt for Population 3 is a forensic investigation on a cosmic scale, piecing together the evidence from the aftermath of their brief, brilliant, and universe-altering lives. While the first stars were the initial pioneers, lighting their solitary beacons in the dark, the true heavy lifting of cosmic reionization likely fell to the first organized structures to form, galaxies. This brings us to our second great mystery. Were the primary drivers of this universal transformation colossal, massive galaxies, or were they vast swarms of tiny, faint dwarf galaxies? This isn't just a question of scale. The answer dictates how we understand the distribution of power in the infant universe and what our most powerful telescopes should be searching for. These early galaxies didn't form randomly. They coalesced at the densest knots in the cosmic web, the intersections of dark matter filaments that had been growing since the Big Bang. Imagine these invisible halos of dark matter as gravitational wells, deep pits in the fabric of space-time that acted as cosmic nurseries. Ordinary matter, hydrogen and helium gas flowed into these wells, cooling and condensing until it eventually fragmented and ignited into stars. A galaxy was born. The more massive the dark matter halo, the more gas it could pull in, and the more stars it could create. These stars, burning hot and fast, would then flood their galactic home with ionizing ultraviolet radiation. But here lies the critical puzzle. Producing the photons is only half the battle. For a photon to contribute to reionization, it must first escape its host galaxy. This concept is known as the escape fraction, the percentage of these high-energy photons that actually manage to break free from the dense clouds of gas and dust within their galaxy and voyage out into the intergalactic medium. If the escape fraction is too low, even a galaxy brimming with brilliant stars would be like a light bulb encased in thick fog, its light trapped and unable to help clear the universal haze. This escape was a tremendously difficult journey. The photons had to run a gauntlet through their own galactic neighborhood, with countless opportunities to be absorbed by a random hydrogen atom and reconverted back into neutral gas, effectively canceling out their ionizing power. This is where the great debate between dwarf and massive galaxies gets truly fascinating. Smaller, dwarf galaxies might have had a crucial advantage. Their gravitational pull was weaker, making it easier for tremendous events like supernova to blow huge holes and channels in their gas clouds. Think of it like punching a hole in a small paper bag versus a giant burlap sack. It's far easier to create an escape route in the smaller, less dense system. These cleared pathways would have allowed ionizing photons to stream out virtually unimpeded, giving even a faint dwarf galaxy an outsized impact on its surroundings. On the other hand, more massive galaxies produced a torrentially larger number of photons. Even if a smaller percentage of them escaped, their raw, overwhelming numbers could have been the dominant force, systematically ionizing vast regions of space around them. This is the core of the mystery that observatories like the James Webb Space Telescope are designed to solve. By staring deep into fields like the Hubble Ultra Deep Field, JWST isn't just looking for any old galaxies, it's conducting a cosmic census of the earliest universe. It's searching for incredibly faint, high redshift dwarf galaxies that previous telescopes could never hope to see, counting their numbers, measuring their brightness, and analyzing their light to estimate how many ionizing photons they were producing. By comparing the population of these tiny dwarfs to the rarer, brighter massive galaxies, astronomers hope to finally weigh their respective contributions and determine which type of galaxy was truly responsible for finishing the job of lighting up the cosmos. The answer will rewire our understanding of how the universe organized itself from darkness into light. But while stars and galaxies were busy lighting their corners of the cosmos, there existed another, far more ferocious source of power in the early universe. Imagine an engine of such incredible violence and brilliance that it could outshine an entire galaxy of stars. This brings us to our third profound mystery, the potential role of quasars and the supermassive black holes that fuel them in the great story of reionization. A quasar, short for quasi-stellar object, is the intensely luminous core of a distant galaxy, and its power comes from a supermassive black hole, a gravitational monster with a mass millions or even billions of times that of our Sun. But unlike the black holes of popular imagination that simply suck everything in, these early beacons were anything but dark, as vast quantities of gas, dust, and even stars spiraled into the black hole's gravitational grip. They didn't just vanish. This material formed a searingly hot, swirling disk of plasma called an accretion disk, heated to millions of degrees through friction and gravitational forces. Before this matter made its final plunge past the point of no return, it released a mind-boggling torrent of energy across the entire electromagnetic spectrum, from radio waves to gamma rays. It is this process that transforms a supermassive black hole into a quasar, effectively turning it into the universe's most powerful lighthouse. The light from a quasar isn't just bright, it's specifically rich in the high-energy, extreme ultraviolet photons that are perfectly tuned to rip electrons away from hydrogen atoms. A single, powerful quasar could flood its entire region of space with more ionizing radiation than 1,000 galaxies combined, potentially clearing enormous spherical bubbles in the neutral hydrogen fog around it. For a long time, astronomers theorized that these cosmic powerhouses might have been the primary drivers of reionization, single-handedly ionizing vast swaths of the early universe with their overwhelming brilliance. However, a major puzzle soon emerged. While quasars are undeniably potent, the critical question is one of population. Were there ever enough of them at these very early times to do the job? Current observations suggest that they were simply too rare. For every bright quasar we've found in the distant universe, we've found thousands of early galaxies. The radiation from all those countless stars added together likely provided the bulk of the photons needed for reionization. Quasars probably played a more specialized, yet still crucial, role. Think of them not as the main workforce, but as the elite specialists. They might have been responsible for ionizing the very largest voids, the most remote and empty regions of space between the vast filaments of the cosmic web, where the combined light from galaxies was too faint to reach. They punched through the last, most stubborn pockets of neutral gas, helping to ensure the universe became fully and uniformly transparent. This leads to one of the most perplexing sub-mysteries of all. How did these supermassive black holes grow to such immense sizes so quickly? We see fully formed quasars with billions of solar masses shining brightly when the universe was less than 1 billion years old. That doesn't give them much time to form from the first generation of stars and then accumulate mind-boggling amounts of matter. Their rapid formation challenges our very understanding of black hole growth and seed formation, hinting at exotic and still unknown processes in the primordial universe. Yet, for all their mystery, quasars provide us with an invaluable tool. Their light acts as a cosmic flashlight. As it travels billions of light years to reach us, it passes through clouds of intergalactic hydrogen. We can analyze the quasar's spectrum, the detailed breakdown of its light, and look for specific gaps or absorption lines where neutral hydrogen has absorbed particular wavelengths. This allows us to create a detailed map of the ionization state of the universe at different epochs. By studying these ancient beams of light, we are effectively reading the history of reionization itself, written in the shadows they cast upon the cosmic fog. This brings us to a mystery that is fundamental to piecing the entire story together, the timeline of this great transformation. We know reionization happened, but when did it begin? How long did it take, and when was the job finally finished? Pinpointing the precise chronology of this era is like trying to solve a cosmic murder mystery where the only clues are 13 billion years old. The evidence we have is powerful, but it often seems to point in slightly different directions, creating a captivating puzzle for cosmologists. One of our most vital pieces of evidence comes from the very beginning of the universe itself, the cosmic microwave background, or CMB. This faint afterglow of the Big Bang, exquisitely mapped by satellites like Planck, is a snapshot of the cosmos when it was just 380,000 years old. At that time, the universe was a hot, dense plasma that suddenly became transparent as it cooled, allowing photons to travel freely for the first time. The CMB shows us a universe that is almost perfectly smooth, with tiny fluctuations that would eventually grow into galaxies. Crucially, the CMB also tells us that at this incredibly early stage, the universe was almost entirely neutral. The reionization process had not yet begun. By studying how these ancient CMB photons were later scattered by free electrons during reionization, the Planck satellite provided a crucial average. It suggested that reionization was likely halfway complete by the time the universe was around 700 million years old, a point we describe as a redshift of approximately 7.5. But when we turn to a different set of clues, the light from the most distant quasars, the story gains a new layer of complexity. The spectra of these brilliant beacons, observed at redshifts greater than 6, show something called the Gunn-Peterson trough. This is a profound and telling silence in the data, a complete absorption of specific wavelengths of light by neutral hydrogen. If the intergalactic medium along the line of sight was fully ionized, this trough would not exist. The light would pass through unimpeded. The presence of a deep Gunn-Peterson trough is like seeing a streetlight completely swallowed by a thick, impenetrable fog. This evidence strongly suggests that at these very high redshifts, corresponding to when the universe was less than 1 billion years old, vast regions of space were still predominantly neutral. The fog was still very much present, so we have two compelling lines of evidence that seem to tell slightly different stories. The CMB gives us a global, averaged measure that points to a midpoint, while the quasar spectra provide direct, local snapshots that show the process was still very much underway at later times. Reconciling these two is a major focus of modern astrophysics. The emerging picture is not one of a simple, instantaneous flip of a switch, but of a prolonged and patchy process. Reionization likely began with small, isolated bubbles of ionized gas forming around the very first stars and galaxies. These bubbles grew, overlapped, and eventually merged like rising air bubbles in a pot of water just before it boils. The timeline, therefore, wasn't uniform across the entire cosmos. Some regions became clear early on, while other pockets of stubborn neutral hydrogen persisted for much longer. Understanding this chronology is not just an academic exercise. It is absolutely crucial for identifying the primary sources of the ionizing photons. If reionization ended very early, it would imply an incredibly efficient and potent source of radiation, perhaps pointing to a dominant population of massive galaxies or an unexpectedly large number of quasars. A later end date, however, might favor a more drawn-out process driven by smaller, fainter galaxies that took longer to accumulate and release their energy. Each new observation from telescopes like JWST which allows us to directly count galaxies from this epoch and measure their ionizing output, helps to refine these models. We are essentially carbon dating the universe's transition from darkness to light, and with every new data point, we get closer to writing the definitive history of our cosmic dawn. This patchwork progression of reionization is our next great mystery. If you were to take a grand tour of the universe during this era, you wouldn't see a uniform, gentle brightening like a cosmic sunrise. Instead, you would witness a chaotic and clumpy transformation, a universe lighting up in fits and starts. The process was profoundly inhomogeneous, unfolding at different rates in different places, and this unevenness holds critical clues about the very sources that powered it. The story begins with the first lonely stars and the earliest, tiniest galaxies. Each one, as it flickered to life, began flooding its immediate surroundings with energetic ultraviolet photons. But these photons couldn't travel far. The universe was still thick with neutral hydrogen, a dense fog that greedily absorbed this radiation. The effect was that each source of light created a small, isolated bubble of clear, ionized plasma around itself, a single bright room in an otherwise dark, sprawling mansion. The size of this bubble was directly tied to the power of its central source. A faint, small galaxy might only manage to clear a modest region of space, while a brilliant quasar could carve out a colossal spherical void, millions of light years across. Over millions of years, these individual bubbles began to grow. As a galaxy formed more stars, its output of ionizing radiation increased, pushing the boundary of its bubble further out into the neutral wilderness. Eventually, the edges of adjacent bubbles began to touch and then overlap, merging into ever larger, connected regions of ionized space. Imagine the process like water slowly soaking into a vast, dry sponge. The first drops create small, isolated wet spots. As more water is added, these spots expand, connect, and finally saturate the entire structure. This is how the universe transitioned, not all at once, but through the gradual merging of countless ionized bubbles until the entire cosmic sponge was soaked through. This bubble-like topology fundamentally shapes how we observe and interpret this ancient epoch. For instance, when we point our telescopes at the most distant quasars, the light we see has traveled for billions of years on a very specific path through the universe. If that path happens to cut through a region that was ionized early on, the light will pass through relatively unscathed. But if its journey took it through a stubborn pocket of the universe that was one of the last to be reionized, that same light will show the strong absorption signature of neutral hydrogen. This means two quasars at the exact same distance from us can tell two very different stories about the transparency of the universe at that time, simply because they look through different parts of the cosmic sponge. It's a powerful reminder that we are not seeing a global average, but a series of individual snapshots. To truly map this complex three-dimensional process, astronomers are turning to a revolutionary technique known as 21-centimeter cosmology. This method relies on a subtle signal from the neutral hydrogen itself. Hydrogen atoms have a tiny energy difference between the spin states of their proton and electron. When an atom transitions between these states, it emits or absorbs a radio wave with a very specific wavelength of 21 centimeters. By tuning massive radio telescope arrays like the Hydrogen Epoch of Reionization Array or the Future Square Kilometer Array to the corresponding frequency for the early universe, scientists hope to do something extraordinary, create a dynamic three-dimensional movie of reionization. These telescopes won't see individual bubbles, but they will detect fluctuations in the 21-centimeter signal across the sky. Regions that are still neutral will glow brightly in this radio light, while the ionized bubbles will appear as dark voids. By observing how this patchwork of light and dark evolves over cosmic time, we will be able to literally watch the bubbles grow and merge. This data will allow us to measure the typical size of the ionized regions at different times, which acts as a direct fingerprint of the sources that created them. Larger bubbles imply more powerful, concentrated sources like big galaxies or quasars, while a universe filled with many small bubbles would point to a dominant population of numerous, faint sources like dwarf galaxies. Understanding this bubble topology is therefore the key to unlocking the entire history of reionization, finally revealing the identity of the primary architects of our transparent universe. While the bubble-like nature of reionization provides a compelling theoretical framework, actually observing this cosmic patchwork directly presents one of the most formidable technical challenges in all of modern astronomy. This brings us to our sixth mystery, the immense promise and staggering difficulty of detecting the 21-centimeter line from the era of reionization. This faint whisper from the ancient universe holds the potential to become our ultimate time machine, offering a dynamic, three-dimensional movie of the cosmic dawn. But extracting it from the cacophony of the cosmos is a task that pushes the very limits of our engineering and ingenuity. The principle itself is elegantly simple. We know that a lone hydrogen atom out in the quiet of space has a tiny intrinsic property. The spin of its single proton and its single electron can be aligned or anti-aligned. The difference between these two states is minuscule, but when an atom flips from the higher energy state to the lower one, it releases a photon with a very specific wavelength, 21 centimeters, which falls in the radio part of the electromagnetic spectrum. During the Dark Ages and the Reionization Era, the universe was filled with a thick fog of this neutral hydrogen, all subtly emitting this specific radio signal. As the universe expands, this light is stretched or redshifted. The signal from the very beginning of reionization has been stretched to much longer wavelengths, while the signal from the end of the era is redshifted less severely. This is the key. By tuning our radio telescopes to different frequencies, we can effectively slice the universe into different cosmic times. Observing a range of frequencies would allow us to stack these slices on top of each other, creating a full three-dimensional map that shows the evolution of ionized bubbles as they grow and merge over hundreds of millions of years. It would be the most direct view of reionization we could ever hope to achieve. However, the reality of this observation is anything but simple. The first and greatest obstacle is the sheer weakness of the signal. After being stretched by the expansion of the universe for over 13 billion years, the 21-centimeter signal from the reionization era is incredibly faint. To put it in perspective, the signal is about 100,000 times weaker than the background radio noise from our own galaxy. This galactic interference, primarily synchrotron radiation caused by electrons spiraling around magnetic field lines, is not just a minor annoyance. It is a deafening roar that completely drowns out the faint cosmic whisper we are desperate to hear. Separating the signal from this foreground noise is like trying to hear a single mosquito buzzing in the middle of a hurricane. This is where the sophisticated technology of modern radio arrays comes in. Projects like the Hydrogen Epoch of Reionization Array, or HERA, in South Africa, and the Future Square Kilometer Array, or SCAR, are not single dishes but vast collections of hundreds of simple radio antennas spread across a landscape. Their power comes from combining signals from all these antennas, a technique called interferometry to create a virtual telescope with a colossal collecting area and incredible resolution. But this introduces another layer of immense difficulty: calibration. Every antenna, every cable, every amplifier has its own slight electronic idiosyncrasies and is affected differently by the Earth's atmosphere. To make a precise measurement, scientists must account for every single one of these variations with extraordinary accuracy. A tiny error in calibration can easily create artificial patterns in the data that look exactly like the cosmological signal we are searching for, leading to a false detection. Furthermore, human-made radio frequency interference, from everything from satellite transmissions to car ignitions, constantly contaminates these pristine radio-quiet zones, adding another layer of pollution that must be meticulously filtered out. The scientific payoff for overcoming these monumental challenges would be nothing less than revolutionary. A clear detection of the 21-centimeter signal would transform our understanding from a collection of theories into a detailed observational science. The statistics of the bubbles, their sizes, their distribution, how they cluster, would act as a direct fingerprint of the sources that created them. For instance, if the ionized regions we see are very large, it would tell us that the ionizing sources were rare but incredibly powerful, like massive galaxies or quasars, capable of clearing huge volumes of space on their own. Conversely, if the map reveals a universe filled with many smaller, closely packed bubbles, it would be strong evidence that reionization was primarily driven by a vast population of much smaller, fainter dwarf galaxies. We could watch the bubbles grow in real cosmic time, precisely dating the start, middle, and end of the entire process, and finally reconciling the different timelines suggested by the cosmic microwave background and distant quasars. This is why the pursuit of the 21-centimeter line remains one of the most intense and thrilling endeavors in cosmology. It is a high-stakes detective story playing out across radio-quiet deserts in South Africa and Western Australia, where teams of scientists are developing increasingly complex algorithms to peel back the layers of foreground noise. Every year, the upper limits on the signal get tighter, constraining our theoretical models and forcing us to think more creatively. The hunt for this signal is a testament to our relentless curiosity, a drive to not just infer the history of our universe, but to witness it directly, mapped across the sky in the faint, redshifted glow of primordial hydrogen. Yet for all their theoretical promise, dwarf galaxies present their own set of profound challenges, turning their potential role into one of the era's most heated debates. The central issue revolves around a delicate and destructive balance. The very supernova that might punch escape routes for photons could also spell doom for the galaxy itself. When a massive star ends its life in a supernova, it doesn't just release light. It unleashes a titanic shockwave that blasts outward at thousands of kilometers per second. In a massive galaxy like our own Milky Way, with its immense gravitational pull and deep potential well, this energy can be absorbed. It might simply stir up the gas, perhaps even triggering new rounds of star formation. But in a tiny dwarf galaxy with a gravitational grip 1,000 times weaker, the effect is catastrophic. This supernova feedback can literally blow the entire reservoir of star-forming gas clear out of the galaxy, ejecting it into intergalactic space. This leaves the dwarf galaxy barren, a ghost ship adrift in the cosmic sea, unable to form new stars. If this happens too quickly, a dwarf galaxy might only manage one brief, intense burst of star formation before it is permanently shut down. It would flash brilliantly for a few million years and then go dark forever, a fleeting contribution to the long, slow process of reionization. This creates a critical timing problem. Did these countless dwarfs all flare up at different times, providing a sustained, universe-wide shower of ionizing photons over hundreds of millions of years? Or did they all light up and then snuff out in a synchronized, short-lived frenzy? The answer depends on the complex and poorly understood physics of how energy propagates through these low-mass systems, a field where computer simulations are our primary guide. State-of-the-art cosmological simulations show both outcomes. Some models produce dwarfs that are indeed quickly quenched by their own feedback, while others show dwarfs with more resilient gas reservoirs that allow for repeated, smaller bursts of star formation. The difference often comes down to the resolution of the simulation and how it models the messy, chaotic physics of supernova explosions and gas cooling. This uncertainty means that the total ionizing budget from the dwarf galaxy population remains one of the largest unknowns in all of reionization science. This is precisely the mystery that the James Webb Space Telescope was built to solve. Its unprecedented infrared sensitivity allows it to do what Hubble never could: directly detect and count these incredibly faint, high redshift dwarf galaxies. JWST is conducting a deep and thorough census of the early universe, looking past the rare, bright galaxies to find the vast, silent majority of tiny systems. By counting their numbers, measuring their colors, and analyzing their light to estimate how many young, hot stars they contain, astronomers can finally calculate their collective output of ionizing photons. The early results are already transforming the debate. JWST is finding far more of these small, faint galaxies at very high redshifts than many simulations had predicted. Every new deep field seems to reveal a previously invisible population of tiny red dots, each one a dwarf galaxy seen at the edge of time. Their sheer abundance suggests that even if each one only contributed a small trickle of radiation, their combined effect could have been a flood, providing a steady and pervasive source of ionizing photons that slowly, patiently cleared the cosmic fog. The case for dwarfs as the unsung heroes of reionization is growing stronger with every new image beamed back from 1,000,000 miles from Earth. Now we arrive at a pivotal and deeply frustrating number in the entire reionization equation, a single parameter so crucial that our entire understanding of this cosmic era hinges upon it, yet so elusive that it remains one of the largest sources of uncertainty in all of cosmology. This is the mystery of the Lyman continuum escape fraction. In simple terms, it's the percentage of those all-important, high-energy ultraviolet photons that actually manage to break free from their host galaxy and travel into intergalactic space to do their job of ionizing hydrogen. Think of it this way: a galaxy can be a brilliant cosmic factory producing a staggering number of ionizing photons from its countless hot, young stars. But if those photons can't escape the factory walls, they are utterly useless to the larger goal of reionizing the universe. The galaxy's light becomes trapped, like a lighthouse enveloped in an impenetrable fog, its beacon visible only to itself. The escape fraction is the measure of how leaky those factory walls are. A value of 0 means the galaxy is a perfect prison for light. A value of 100% means every single photon produced gets out. The problem is, for the distant early galaxies we're interested in, this number is incredibly difficult to measure, and even our best estimates range from a paltry 1% to a potentially decisive 20% or more. The primary reason for this difficulty is a cruel cosmic irony. The very same neutral hydrogen atoms we want to study are the very thing that prevent us from seeing the photons that ionize them. The intergalactic medium between us and a high redshift galaxy is still littered with patches of neutral hydrogen, even after reionization. These atoms are perfectly tuned to absorb the specific wavelengths of light we need to observe the Lyman continuum. So, by the time the light from a distant galaxy travels billions of light years to reach our telescopes, any trace of its escaping ionizing radiation has been completely scrubbed clean from its spectrum. It's like trying to study a blue dye by looking at a river downstream after the water has passed through a perfect filter. The dye is gone, and we're left to guess its original color and concentration. Faced with this direct observational wall, astronomers have become cosmic detectives, developing ingenious indirect methods to estimate the escape fraction. One common approach is to look for telltale signatures within the galaxy itself. The journey of an ionizing photon is a violent one. As it fights its way out of the galaxy, it can leave forensic evidence in the light that does reach us. For example, the way hydrogen gas within the galaxy absorbs light at slightly longer wavelengths can indicate whether there are clear, channeled pathways, perhaps carved by stellar winds and supernova through which the ionizing photons could have fled. The relative strength of certain emission lines produced by the galaxy's gas can also act as a gauge for how much of the harder radiation is leaking out versus being absorbed locally. Another powerful, though rare, technique is to use the universe's own natural telescopes, gravitational lenses. When a massive foreground galaxy cluster sits directly between us and an extremely distant galaxy, its immense gravity bends and magnifies the background galaxy's light, sometimes amplifying it by a factor of 10 or more. This magnification boost is our best chance. It allows telescopes like Hubble and JWST to see a distant galaxy in far greater detail than would otherwise be possible, potentially allowing us to detect the faint, precious signal of escaping Lyman continuum photons just as they leave the galaxy, before they are absorbed by the intergalactic medium on their long journey to us. A handful of these lucky lensed systems have provided some of the most direct and valuable measurements of escape fractions in the early universe. The immense consequence of this single number cannot be overstated. The uncertainty in the escape fraction propagates directly into a vast uncertainty in the entire reionization budget. The calculation of whether early galaxies produced enough escaping photons to get the job done. If the average escape fraction was only 5%, then we would need a much larger population of galaxies than if it were 20%. A low value might force us to reconsider if we've missed an entire population of sources, or if something else like faint quasars played a bigger role. A high value would solidify the case for galaxies as the dominant engine. Getting this number right is the key to balancing the cosmic books, and until we can constrain it better, the story of how the universe was illuminated remains frustratingly incomplete. But to truly understand why these first sources of light appeared where they did, we must look beyond the stars and gas to the invisible scaffolding that dictated the entire structure of the early universe. This brings us to a deeper, more fundamental mystery, the profound role of dark matter. While dark matter itself does not emit, absorb, or scatter light, making it completely invisible to our telescopes, its gravitational influence was the master architect that drew the blueprint for cosmic reionization. The entire process was orchestrated within an unseen framework of dark matter halos, and the very nature of this mysterious substance may have determined how quickly the lights could turn on. The story begins just after the Big Bang, with a universe filled with a nearly uniform soup of dark matter and regular matter. But thanks to tiny quantum fluctuations imprinted in the first instant of time, this soup wasn't perfectly smooth. Some regions were ever so slightly denser than others. Over millions of years, gravity acted on these imperfections, relentlessly pulling more and more matter into these dense spots. The dark matter, being unaffected by the pressure of radiation, was the first to collapse, forming vast, intricate webs of filaments and knots known as the cosmic web. At the intersections of these filaments, dark matter coalesced into stable structures called halos, gravitational wells of pure, invisible mass. It was at the centers of these halos that the ordinary atomic matter, the hydrogen and helium gas, was finally able to cool, condense, and collapse to form the very first stars and galaxies. The distribution of galaxies was not random. It was a perfect tracing of this underlying, invisible architecture of dark matter. Where a massive dark matter halo formed, a galaxy was destined to bloom. Reionization, therefore, did not begin uniformly across the cosmos. It ignited first at these densest knots in the cosmic web, where the gravitational wells were deepest and could attract gas the fastest, creating the powerful early sources that lit the first sparks in the darkness. This leads to a fascinating and ongoing debate in cosmology that directly impacts our reionization story. Is dark matter cold or could it be warm? The standard model, known as cold dark matter or CDM, posits that dark matter particles move slowly and are very massive, which allows them to clump efficiently on extremely small scales. This model predicts a universe that should be teeming with an enormous number of tiny dark matter halos, far more numerous than the galaxies we see around us today. In this view, the early universe should have been filled with a vast population of low-mass halos, each a potential site for a small, faint galaxy. If even a fraction of these tiny halos hosted galaxies that leaked ionizing photons, they could have provided a pervasive, widespread source of radiation that slowly and steadily reionized the universe. However, an alternative idea known as warm dark matter, or WDM, suggests the particles are lighter and faster moving. This slight difference has a dramatic consequence. It smooths out the smallest scales of the cosmic web. The gravitational wells that could form the tiniest halos are wiped out by the particle's higher velocity. A warm dark matter universe would have far fewer of these small halos, meaning a significantly reduced population of the faint dwarf galaxies that are prime suspects in the reionization mystery. If WDM were correct, the early sources of light would have been more isolated and dominated by rarer, larger galaxies that formed in the bigger halos that survived the smoothing effect. This would paint a very different picture of reionization, one that started later and was driven by more concentrated, powerful bursts of radiation from massive galaxies, rather than a gentle universe-wide shower from countless dwarfs. The timing and topology of reionization, therefore, act as an indirect test for the very nature of dark matter itself. By counting the number of small, early galaxies with JWST and mapping the bubble sizes with future radio telescopes, we are effectively conducting a census of the smallest dark matter halos, probing the fundamental properties of the universe's most elusive substance. But the relationship between dark matter and reionization is not a one-way street. It's a dynamic feedback loop. The reionization process, once ignited, fought back against the very structures that gave it birth. As those first bubbles of ionized plasma grew, they didn't just make the universe transparent, they made it hot. The same ultraviolet photons that ripped electrons from atoms also transferred enormous energy to them, heating the intergalactic gas from a frigid few tens of degrees to a scorching 10,000 degrees or more. This heating had a dramatic consequence for the future of galaxy formation, particularly for the small, faint systems that may have started the process. For a galaxy to form, cool gas must be able to flow into a dark matter halo and condense into stars. But after reionization, the gas outside galaxies was no longer cold and neutral, it was hot and ionized. Hot gas has much higher pressure and is far more resistant to gravitational collapse. More critically, the intense heat made it much harder for the gas to cool down and condense into the dense clouds required for star formation. For the most massive halos with their deep gravitational wells, this was not a significant problem. Their powerful gravity was more than strong enough to overcome the increased pressure and continue pulling in gas. But for the smallest dark matter halos with their shallow gravitational potentials, it was a catastrophe. They simply lacked the gravitational muscle to acquire new gas from the hot, pressurized intergalactic medium. Reionization effectively pulled up the drawbridge, preventing any new gas from falling into the smallest halos and stifling the formation of new dwarf galaxies. This process, known as photoheating suppression, may explain a curious modern-day observation: why there are far fewer small galaxies orbiting around the Milky Way than the standard cold dark matter model predicts. The first galaxies literally changed the rules of the game, heating their environment so much that they prevented more of their own kind from ever forming. A poignant example of the universe regulating its own growth and shaping its future evolution from the very beginning. This transformative heating of the intergalactic medium did far more than just clear away an ancient fog. It fundamentally reshaped the future of cosmic structure, creating a lasting impact that echoes through billions of years of galaxy evolution. This process, known as reionization feedback, is one of the most significant legacies of the cosmic dawn, effectively setting a universal minimum size for galaxy formation and leaving a fossil record we can still observe today in our own galactic backyard. To understand this feedback, imagine two competing forces: gravity, which strives to pull gas inward to form stars, and pressure, which pushes back against that collapse. Before reionization, the vast reservoirs of hydrogen gas between galaxies were cold and neutral, making them exceptionally easy to compress. Even the shallow gravitational well of a relatively small dark matter halo could easily pull in this cold gas, allowing it to cool, condense, and eventually form stars, birthing a dwarf galaxy. But the reionization process changed the rules of the game completely. The same ultraviolet photons that ionized the hydrogen also transferred a tremendous amount of energy to it, heating the intergalactic gas from a frigid few tens of degrees to a scorching 10 to 20,000 degrees Kelvin. This newly ionized and heated gas was now a high-pressure plasma, fiercely resistant to gravitational collapse. For the most massive dark matter halos with their incredibly deep gravitational potentials, this was a minor inconvenience. Their powerful gravity was more than strong enough to overcome the gas pressure and continue pulling in fresh material. But for the smallest halos with their weak gravitational pull, it was an insurmountable barrier. They simply lacked the strength to acquire new gas from this hot, pressurized environment. Reionization effectively pulled up the cosmic drawbridge, severing the gas supply to the smallest potential galaxies and stifling their growth before they could even properly form. This theoretical prediction leads to a very specific and testable outcome for our modern universe: a profound lack of small, faint galaxies, especially when compared to the vast number of small dark matter halos that theories like cold dark matter predict should exist. The most compelling evidence for this comes from right here in the local group, from the population of tiny satellite galaxies orbiting the Milky Way and Andromeda. Cosmological simulations run without the effects of reionization feedback produce a veritable swarm of small dark matter subhalos around a galaxy like ours, and many of these should have been able to form stars and become visible dwarf galaxies. But when we look up at the sky, we only see a few dozen such satellites, not the hundreds or even thousands the simulations might otherwise suggest. This glaring discrepancy, known as the missing satellites problem, is strongly attributed to the effects of reionization. The heating from the ultraviolet background effectively sterilized the smallest halos, preventing them from ever becoming galaxies we can see. The satellites we do see are likely the survivors, the ones that were either massive enough to withstand the pressure, or that formed most of their stars very early on, before the reionizing background reached its peak intensity and shut down star formation for good. The fossil record of these surviving dwarfs provides even more subtle clues. The characteristics of a dwarf galaxy's stellar population can act as a cosmic clock, telling us when it formed the bulk of its stars. For many of the Milky Way's faintest satellites, that clock appears to have stopped ticking almost simultaneously. They contain only ancient stars, all remarkably similar in age, with no evidence of any significant star formation after the universe's first billion or so years. This is precisely what we would expect if reionization's heat wave swept through the local group, cutting off their gas supply and leaving them as frozen relics of a much earlier time. Furthermore, the three-dimensional distribution of these satellites might hold clues about the hardness of the ionizing background, a term that refers to the proportion of high-energy photons in the radiation field. A harder background, rich in extreme UV light from sources like quasars or very massive stars, would have been more efficient at both ionizing and heating the gas to higher temperatures, potentially suppressing galaxy formation even more effectively. By studying the properties, numbers, and distribution of these ancient satellite systems, astronomers are indirectly reading the conditions of the reionization era itself, using the survivors of that cosmic revolution to understand the forces that shaped it. Yet even as we map these vast cosmic structures and their enduring legacy, we uncover a deeper, more subtle puzzle hidden within the light itself, a puzzle of quality, not just quantity. While the first stars and galaxies provided the flood of radiation needed to strip electrons from hydrogen, reionization's final act required something even more potent. This brings us to our 11th mystery, the search for the sources of hard ionizing photons, the elite radiation that finished the job by tackling the universe's most stubborn atoms. To understand why this is so crucial, we need to look at the periodic table of the early universe. After hydrogen, the next most abundant element was helium, forged in the Big Bang right alongside it. But ionizing helium is a much tougher task than ionizing hydrogen. A hydrogen atom holds onto its single electron with a certain energy, which we measure as 13.6 electron volts. To liberate that electron, a photon must carry at least that much energy. Helium, with 2 protons in its nucleus, holds its 2 electrons much more tightly. Stripping the first electron requires 24.6 electron volts, and removing the second, a process called double ionization, demands a staggering 54.4 electron volts. This is the difference between prying open a simple lock and cutting through a bank vault. The photons capable of this feat occupy the highest, most extreme end of the ultraviolet spectrum, and their presence is what we mean by a hard ionizing background. The timing of helium reionization provides a vital clue. While hydrogen reionization was largely complete by the time the universe was around 1 billion years old, evidence from the spectra of distant quasars suggests that helium reionization happened much later, concluding when the universe was roughly 2 to 3 billion years old. This delay implies that the sources responsible for finishing this job were different from the pioneers that started it. They had to appear later and possess a uniquely ferocious output of high-energy radiation. For a long time, the prime suspects were obvious: quasars. These monstrous engines, powered by supermassive black holes, are factories for extreme UV photons. Their accretion disks are so energetic that they produce a broad spectrum of light, rich with the hard radiation needed to double ionize helium. A universe with a growing population of quasars around this later time fits the evidence neatly. However, a compelling alternative theory has emerged, one that points the finger back at galaxies, but not the ordinary ones we see today. The key may lie with a generation of stars even more extreme than the first population 3 giants. As the universe evolved, stars began to form from gas that was still extremely pristine, but not perfectly pure. These second-generation stars, sometimes called population 2.5, would have had very low metallicity, meaning almost no elements heavier than helium. Without heavier elements, which are very efficient at cooling gas and allowing it to fragment into smaller stars, star-forming clouds could have continued to collapse into truly massive behemoths. Furthermore, the lack of metals in the stars themselves changes their internal physics. Metals in a star's atmosphere absorb radiation and then re-emit it at lower energies, effectively softening the star's output. A very low metallicity star lacks this internal blanket. It burns hotter and brighter, and its radiation shifts toward the higher energy, harder end of the spectrum. A galaxy teeming with such stars could potentially produce a significant flux of the very photons needed to ionize helium, acting as a distributed network of hard radiation sources across the cosmos. This debate is far from settled, and it represents a major frontier in our understanding. The hardness of the ionizing background, the ratio of high energy to lower energy photons, is a direct fingerprint of the sources that created it. A background dominated by quasar light would have a very hard spectrum, while one produced primarily by hot stars would be somewhat softer. By studying the absorption lines in the spectra of distant quasars and galaxies, astronomers can indirectly measure this hardness at different cosmic times. They look for the subtle fingerprints of elements like silicon and carbon, which require different energy thresholds to ionize. The relative abundances of these different ionization states act as a cosmic chemical gauge, telling us the intensity of the high-energy radiation field that bathed the gas. Unraveling this mystery is essential because it doesn't just tell us what finished reionization. It reveals the changing balance of power in the adolescent universe, showing whether black holes or stellar populations truly dictated the final clearness of the cosmic expanse. After the universe-wide firestorm of ionization had raged for hundreds of millions of years, the cosmic landscape was utterly transformed. Vast, connected regions of ionized plasma now dominated, with brilliant galaxies and quasars shining like beacons across the clear expanse. But the job was not yet finished. Scattered throughout this newly transparent universe remained the last holdouts, the final bastions of pristine darkness, isolated pockets of neutral hydrogen that had somehow resisted the relentless tide of radiation. These were not the sparse, diffuse clouds of the early universe, but rather the most resilient and stubborn structures, and their final evaporation marks the official end of the reionization era. So what were these last neutral patches like? They weren't necessarily random. Theory and simulation suggest they fell into two primary categories. The first were the cosmic dens, regions of unusually high density. Imagine a massive, cold cloud of hydrogen, so dense that its outer layers acted as a self-shielding cloak. As ionizing photons streamed in, the outer atoms would be stripped away, but the sheer number of atoms deeper inside created a defensive barrier. The photons would be absorbed one after another, their energy dissipated before they could reach the heart of the cloud. It was a losing battle for the cloud, as the ionizing background intensity was steadily increasing, but it was a slow and arduous process to erode such a dense object. The second type of final holdout was the exact opposite, the cosmic boondocks. These were extremely remote voids, regions so far from any major galaxy or quasar that the local ionizing radiation field was exceptionally weak. Here, in the deepest, most empty reaches of the cosmic web, neutral hydrogen could persist simply because the flood of photons had become a faint and manageable trickle by the time it reached these distant outposts. The increasing intensity of the ionizing background during these final stages created a fascinating and violent environment within and around these last neutral islands. The boundary between an ionized bubble and a neutral patch, known as an ionization front, would have been a scene of intense astrophysical activity. As the front advanced into the neutral gas, it would heat it rapidly, creating shock waves and potentially triggering secondary waves of star formation in the compressed gas at its edges. For the gas inside these final pockets, it was a race against time. Could it collapse under its own gravity to form new stars or even a new dwarf galaxy before the encroaching radiation field heated it up and ripped it apart? In many cases, the radiation won, sterilizing the gas and preventing the birth of what might have been a new system of stars. How can we possibly observe this specific end phase of reionization, a period that concluded over 12 billion years ago? Our most powerful tool is once again the light from the most distant quasars and galaxies. As their light journeys towards us, it passes through these final neutral regions. The interaction leaves a specific and telltale signature in the quasar's spectrum known as the damping wing of the Lyman alpha line. To understand this, recall that the Gunn-Peterson trough shows near total absorption when the light path is through a largely neutral medium. The damping wing is a subtler effect that appears when the light source itself is embedded inside one of the very last large neutral patches. In this scenario, the neutral hydrogen surrounding the quasar doesn't just create a sharp absorption line. It imposes a broad, smooth, sloping suppression on the blue side of the Lyman alpha emission line. This smooth damping effect occurs because the cloud of neutral gas is so vast and dense that it doesn't just absorb the precise wavelength corresponding to its rest frame. It absorbs a wide range of wavelengths due to the natural broadening of the absorption line in such a dense environment. Detecting this specific damping wing signature is like finding a fossilized air bubble in amber. It proves the quasar was shining at a time when it was still surrounded by a significant reservoir of neutral hydrogen, right at the closing moments of the reionization era. Finding these rare systems is a primary goal for the James Webb Space Telescope. By identifying quasars and brilliant galaxies at record-breaking redshifts, astronomers can then perform a detailed spectroscopic analysis of their light, hunting for the distinctive smoothing signature of the damping wing. Each confirmed detection acts as a precise timestamp, telling us that at that particular point in cosmic time, that region of the universe was still not fully clear. By gathering enough of these timestamps from different parts of the sky, we can finally map the precise endgame of reionization, understanding not just when it ended on average, but how the last pockets of neutrality finally succumbed to the pervasive and growing light of the first cosmic structures. While the first stars ignited a cosmic revolution, it's crucial to understand that their birth marked the beginning of a distinct era, not the reionization process itself. This distinction brings us to our 13th mystery, the nuanced relationship between the cosmic dawn and the subsequent epoch of reionization. Think of the cosmic dawn as the moment a single match is struck in a vast, dark cavern. It creates a point of light, but it doesn't immediately illuminate the entire space. This period encompasses the formation of the very first stars, known as Population 3, and the earliest, faintest proto-galaxies. Their light was the first to pierce the pervasive darkness of the universe's dark ages, but for a considerable time that light was largely trapped. The universe was so thick with neutral hydrogen that these initial beacons could only carve out small, isolated bubbles of ionized plasma around themselves, perhaps only a few hundred light-years across. They were lonely outposts in an otherwise opaque cosmos. The epoch of reionization, in contrast, was the moment the entire cavern caught fire. It was the large-scale, universe-wide process where those isolated bubbles grew, merged, and eventually overlapped to create a fully ionized and transparent intergalactic medium. This was not an instantaneous flip of a switch, it was a prolonged and patchy transition. A central question then is the timing. Was there a significant delay between the first flickers of the cosmic dawn and the full-blown firestorm of reionization? Current evidence suggests the answer is yes. The first stars might have formed astonishingly early, perhaps when the universe was only 100 million years old. However, the process of reionization, as measured by the cosmic microwave background and quasar spectra, didn't reach its midpoint until the universe was around 500 to 700 million years old. This implies a gap of several hundred million years between the first light and the large-scale clearing of the fog. This delay is the heart of the mystery. What triggered the transition from a few isolated bubbles to a full-scale universal process? The initial sparks of the cosmic dawn were not enough on their own. Something had to change to allow the process to accelerate. The key likely lies in a combination of factors that gradually built up over time. First, there was the sheer accumulation of sources. While the first stars lived short, violent lives, their deaths in spectacular supernova explosions seeded their surroundings with the first heavy elements. This pollution fundamentally changed the physics of subsequent star formation. Gas enriched with even a tiny amount of metals can cool much more efficiently, allowing it to fragment into a greater number of smaller, longer-lived stars. This meant subsequent generations of galaxies could form stars more efficiently and for longer durations, steadily increasing the total output of ionizing radiation across the cosmos. Second, the architecture of the universe itself was evolving. The underlying cosmic web of dark matter was maturing. Small dark matter halos were merging to form larger, more massive structures. These bigger halos could pull in more gas and hold onto it more tightly, allowing for the formation of more substantial and luminous galaxies. The shift wasn't just in the number of sources, but in their power. The emergence of these first small galaxies, and slightly later the first quasars, provided the sustained and intense radiation needed to expand the ionized bubbles dramatically. Furthermore, the feedback from the first stars and supernova played a critical and self-regulating role in this pace. The very same supernova that enriched the gas also unleashed tremendous amounts of energy, blowing powerful winds that could both enable and hinder the process. On one hand, these winds could blow away the dense gas clouds surrounding young stars, literally punching holes in the galactic walls and creating crucial escape routes for ionizing photons. This positive feedback increased the escape fraction, allowing more photons to contribute to reionization. On the other hand, these winds could also be incredibly destructive. By ejecting the star-forming gas entirely from small dwarf galaxies, this negative feedback could temporarily shut down star formation, quenching a galaxy's ability to produce new photons and potentially slowing the overall progress in certain regions. The pace of reionization was therefore not a smooth acceleration but a complex tug of war between the birth of new light sources and the disruptive, yet sometimes helpful, feedback from the first generations of stars. It was this delicate balance between creation and destruction that ultimately governed the timeline, determining how long it took for the universe to finally emerge from its dark, neutral cocoon into the brilliant, transparent expanse we see today. But this transformation from a cold, dark cosmos to a brilliant, transparent one came with a profound and lasting side effect. It left the universe not just clear but searingly hot. This brings us to a thermal mystery locked within the ancient gas between galaxies. The process of reionization was far from gentle. It was a violent, energetic upheaval. Every time a high-energy ultraviolet photon ripped an electron away from a hydrogen atom, it didn't just change the atom's state. It transferred a significant amount of kinetic energy to the newly freed particles. Think of it like countless microscopic explosions happening all across the cosmos. This energy didn't just disappear, it was converted into heat, raising the temperature of the entire intergalactic medium from a frigid few tens of degrees Kelvin to a blistering 10 to 20,000 degrees. This intergalactic gas became a thin, ultra-hot plasma that has persisted for billions of years, and its precise temperature now acts as a fossilized thermometer, recording the intensity and nature of the forces that heated it. The mystery arises when we compare this fossil temperature to our theoretical predictions. Many sophisticated computer simulations of the reionization process, which assume it was primarily driven by hot stars in galaxies, predict that the intergalactic gas should have cooled down significantly by the present day. The expansion of the universe alone should have caused this plasma to adiabatically cool, much like a gas expanding in a container loses heat. However, when astronomers actually measure the temperature of this ancient gas using a powerful technique called the Lyman alpha forest, they find it is often warmer than these models predict. The Lyman alpha forest is the intricate pattern of absorption lines seen in the spectra of distant quasars. As the quasar's light travels through the cosmic web, clouds of hydrogen at different distances absorb specific wavelengths, creating a forest of lines. The width of each individual absorption line is directly related to the temperature of the hydrogen cloud that caused it. Hotter gas produces broader lines due to the faster, more energetic motion of its atoms. These measurements suggest that the intergalactic medium retained more of its primordial heat than expected, pointing to a more intense or different kind of heating process during reionization. So what kept the universe's gas so unexpectedly toasty? One compelling explanation points to the nature of the ionizing sources themselves. Perhaps reionization wasn't just driven by stellar radiation, but was also significantly influenced by a harder, more energetic source of photons. This is where quasars re-enter the story. The accretion disks around supermassive black holes produce a much broader spectrum of light than stars, including a copious amount of extreme ultraviolet and even soft X-ray radiation. These hard photons carry significantly more energy than the UV photons from stars. When they ionize atoms, they transfer a much larger kick of energy to the liberated electrons, heating the surrounding gas to a higher temperature. If quasars contributed a substantial portion of the ionizing background, even if they were not the majority source, their harder radiation could have imprinted a higher residual heat onto the intergalactic medium, a thermal signature that has endured for over 12 billion years. An alternative and equally fascinating possibility is that the timing of reionization holds the key. The quick reionization model suggests the process was more rapid and intense than some simulations assume. If reionization happened in a swift, explosive manner, the heating would have been more sudden and violent. In this scenario, the universe didn't have time to dissipate the immense heat through various cooling processes before the expansion of space took over. The intergalactic gas was essentially flash-heated and then left to cool on a timescale dictated by the universe's expansion, locking in a higher baseline temperature. This would imply an incredibly efficient and powerful source of ionizing photons that worked with startling speed. A conclusion that would again force us to re-evaluate the true power of the first galaxies or the previously underestimated role of early quasars. By reading this fossilized temperature record encoded in the Lyman alpha forest, astronomers are therefore not just measuring a number, they are uncovering vital clues about the duration, intensity, and very sources of the event that shaped the transparent universe we inhabit today. While the densest knots of the cosmic web were the first to blaze with light, the story of reionization was written across the entire universe, including its most barren and empty regions. This leads us to consider the immense cosmic voids, the vast, underdense deserts that stretch for hundreds of millions of light years between the glittering filaments of galaxies. In these near emptinesses, the rules of reionization were fundamentally different, creating an environment where the final whispers of neutral hydrogen could persist for eons longer than anywhere else. Imagine the challenge of ionizing a void. The process in a dense galaxy cluster was a relentless, overwhelming assault. A brilliant quasar or a tightly packed group of massive galaxies could flood its local neighborhood with such an intense concentration of radiation that the surrounding hydrogen was ionized almost instantly. But in a void, the sources of light are incredibly rare and often much fainter. The radiation field there is not a torrent but a faint, diffuse glow, the combined and greatly weakened light from countless distant galaxies in the far-off walls of the cosmic web. For a photon to contribute to ionizing a void, it must embark on an epic journey, traveling for tens of millions of years through the already ionized intergalactic medium before finally reaching this final frontier of neutrality. This journey is not without risk. Even in a clear universe, a photon has a small chance of being absorbed by a stray atom, and the sheer distance increases the odds of such a random encounter. This leads to a fascinating possibility that reionization progressed in an inside-out fashion. The dense regions ionized first from the inside, powered by their own prolific sources. The voids, by contrast, were likely ionized from the outside. Their clearing was not a local event but a slow, patient infiltration as radiation seeped in from the surrounding, brighter structures over hundreds of millions of years. Because of this external and delayed process, it is entirely plausible that significant pockets of pristine, neutral hydrogen survived in the deepest, most isolated voids long after the rest of the universe had become fully transparent. These regions would have been the last refuges of the cosmic dark ages, fossil clouds preserving the conditions of the universe before the first starlight ever shone. Detecting these ancient relics is a primary goal for the next generation of radio telescopes. The 21-centimeter signal from the post-reionization universe isn't supposed to exist. The gas should be ionized and thus invisible at that wavelength. But if neutral patches lingered in voids, they would create a faint, specific kind of radio signature. The upcoming square-kilometer array will be powerful enough to scan these immense empty regions, not to map bubbles from the past, but to hunt for these solitary, fading whispers of neutral hydrogen. Finding them would be like discovering a living fossil, a coelacanth from the cosmic dawn that somehow survived the great ionization. their very presence and their distribution would provide a crucial test for our models. It would tell us how efficient the universe was at completing the reionization process in its most remote corners and constrain the mean free path of those heroic ionizing photons that traveled such incredible distances to finish the job. Now we come to a central and deeply puzzling question that has long troubled cosmologists, a mystery that strikes at the very heart of our understanding of the reionization process. It's essentially a cosmic accounting problem, and the books for a long time just didn't seem to balance. We call this the ionizing photon budget shortfall. To complete reionization by a redshift of 6, when the universe was just under 1 billion years old, we can calculate the minimum number of ionizing photons that must have been produced and, crucially, that must have escaped into intergalactic space per second. It's a staggering number, but the universe had hundreds of millions of years to do it. The problem was that when we added up the contributions from all the high redshift galaxies and quasars we could see with telescopes like Hubble, we kept coming up short. The math simply didn't work. It seemed there was a missing source of power, a hidden wellspring of radiation that we hadn't yet accounted for in our models of the early universe. This shortfall forced astronomers to confront several uncomfortable possibilities. The first and most straightforward solution is that our census of the early universe was wildly incomplete. Our telescopes simply weren't powerful enough to see the vast majority of the population. Think of it like trying to count all the fireflies in a massive field at night with a weak flashlight. You might see a few dozen of the brightest ones close to you, completely missing the thousands of fainter ones flickering in the distance. This is precisely the bias that plagued us. The galaxies that Hubble and other observatories could detect at these incredible distances were the rare, bright, massive ones, the cosmic celebrities. But what if the real workhorses were the countless faint dwarf galaxies, a silent majority too dim for our instruments to register? If they existed in the numbers that some theories predicted, their combined ionizing output could have been immense, easily closing the budget gap. A second possibility is that we severely underestimated the efficiency of the galaxies we could see. This brings us back to that critical and elusive number, the escape fraction. What if the average escape fraction wasn't a conservative 5 or 10%, but was significantly higher in the early universe? Perhaps the conditions in these primordial galaxies were uniquely conducive to letting light flee. With stronger stellar winds from hotter stars, a more turbulent interstellar medium, and a lack of dust to absorb photons, maybe these galaxies were incredibly leaky, with escape fractions pushing 20, 30, or even 50%. A higher escape fraction means that for every 100 photons a galaxy produced, far more of them were actually available to ionize the cosmic fog, dramatically increasing the efficiency of each known source and potentially resolving the shortfall without needing to find a single new galaxy. Then there are the more exotic solutions. Could there have been other, overlooked sources of ionizing radiation at play? One intriguing candidate is a population of objects within galaxies themselves, X-ray binaries. These are systems where a neutron star or black hole is voraciously feeding on material from a companion star, producing intense X-ray radiation in the process. While individual X-rays aren't as efficient at ionizing hydrogen as UV photons, they are incredibly penetrating. They could have preheated large regions of gas, making it easier for subsequent UV radiation to finish the ionization job, effectively increasing the overall efficiency of the process. Even more speculative ideas involve the very nature of dark matter. Could certain theoretical types of decaying or annihilating dark matter particles have released energy in the form of ionizing photons? This remains a highly hypothetical solution, but it underscores the depth of the mystery scientists were willing to consider fundamental new physics to balance the cosmic budget. This is where the James Webb Space Telescope enters the story as a revolutionary arbiter. Its primary mission is to conduct the deepest, most complete census of the early universe ever attempted. By staring for days into tiny patches of sky like the Hubble Ultra Deep Field, but with its vastly superior infrared vision, JWST is peering past the bright celebrities and into the realm of the faint multitude. And the results are already transformative. JWST is discovering a breathtaking number of galaxies at redshifts greater than 10, corresponding to when the universe was less than 500 million years old. Many of these systems are small, faint, and brimming with young, hot stars, exactly the kind of population theorists predicted was needed to provide the missing photons. With every new deep field image, the number of known galaxies in the early universe skyrockets, strongly suggesting that the shortfall wasn't a failure of theory, but a limitation of our technology. We weren't wrong about the universe, we just couldn't see most of it. JWST is now turning on the lights, revealing the countless unsung heroes that provided the relentless rain of photons needed to lift the cosmic veil right on schedule. Yet this cosmic architecture was not a static blueprint. It was a dynamic and evolving structure that shaped the speed and pattern of reionization itself. The clustering of these early sources meant that the first sparks of light did not appear at random. They ignited in concentrated hubs where the gravitational pull was strongest. A solitary galaxy might only manage to carve out a small, isolated bubble of ionized plasma around itself. But when galaxies formed in tight-knit groups, their individual bubbles quickly grew and merged into colossal, connected regions of transparency. These were not just bubbles, they were massive ionized caverns within the neutral hydrogen fog. The effect was profound. In a highly clustered environment, reionization could proceed with startling efficiency. The ionizing radiation from multiple galaxies worked in concert, their combined output creating a powerful local radiation field that could overwhelm and clear the neutral gas far more rapidly than any single source could achieve alone. This collaborative clearing meant that regions with a high density of galaxies likely became transparent much earlier than more sparsely populated voids, accelerating the overall timeline of the process and creating a highly uneven patchwork universe during the transition. The degree of this clustering acts as a powerful diagnostic tool, a key that can unlock the specific history of reionization. If the earliest galaxies were strongly clustered, we would expect to see a very particular pattern in the 21-centimeter maps we hope to obtain. The ionized bubbles would be large and irregular from the very beginning, reflecting the grouped nature of their sources. The signal would show a dramatic contrast between vast, dark regions of neutrality and equally vast, clear regions of ionization. Conversely, if the first sources were more uniformly distributed across the cosmos, the process would have been far more gradual and homogeneous. The bubbles would have been smaller and more numerous, growing slowly and steadily until they finally overlap. The 21-centimeter signal in this scenario would appear far more granular and fine-textured. This is crucial because the observed pattern of bubbles breaks a fundamental degeneracy in interpreting the radio data. A large bubble could be created by a few incredibly powerful sources or by a dense cluster of many weaker ones. By independently measuring the clustering of galaxies with instruments like the James Webb Space Telescope, we can distinguish between these possibilities. If JWST finds that early galaxies are highly clustered, then large bubbles in the 21-centimeter map directly confirm that grouping. If galaxies are not clustered, then large bubbles must instead point to the presence of extraordinarily rare and luminous objects such as quasars. This is precisely the groundbreaking work JWST is now undertaking. By conducting deep, wide-field surveys, it is not just counting individual galaxies at the edge of time. It is meticulously mapping their positions in three-dimensional space. Astronomers are analyzing these exquisite maps to measure the precise clustering strength of these primordial systems, how likely they are to have neighbors compared to a random distribution. Early results are already hinting that galaxy clustering at very high redshifts is significant, suggesting that the first ionized bubbles may have grown large and merged quickly in the densest nodes of the cosmic web. This independent measurement provides the essential context needed to decode the future 21-centimeter signal from arrays like the Square Kilometre Array. Together, these two lines of evidence will weave a complete story, telling us not just when the universe became transparent, but how the specific spatial arrangement of its first luminous structures dictated the pace and pattern of this universal metamorphosis. We are moving from simply knowing the timeline to watching the event unfold in its full, structured complexity, seeing the cosmic web itself light up node by connected node. Before the first stars ever flickered to life, before the cosmic web began to glow with the light of galaxies, the universe existed in a state of profound and perfect darkness. This period, stretching from roughly 380,000 years after the Big Bang to the birth of the first stars, is known as the Dark Ages. It was a cosmos without a single source of light, a silent, expanding void filled only with a pristine, neutral fog of hydrogen and helium gas, slowly cooling in the aftermath of the primordial fireball. To understand the Cosmic Reionization Era, we must first appreciate this long, quiet prelude, the blank canvas upon which the first points of light would eventually appear. This era began with the release of the cosmic microwave background, the moment the hot plasma of the early universe cooled enough for protons and electrons to combine into neutral atoms, rendering the cosmos transparent for the first time. But this transparency also meant the universe was plunged into utter blackness. With no stars, no galaxies, and no other luminous objects, the only energy was the fading afterglow of the Big Bang itself, stretching into longer and longer infrared and radio wavelengths as space expanded. For millions of years, the universe was a remarkably simple and lonely place, a vast sea of gas that was almost perfectly smooth, but not quite. Those tiny fluctuations in density imprinted on the cosmic microwave background were the only seeds of structure in an otherwise featureless expanse. Gravity is a patient force, and it began to work immediately on these minute imperfections. Slightly denser regions of dark matter, completely invisible to us, had a slightly stronger gravitational pull. Over eons, they began to gently tug the surrounding hydrogen and helium gas toward them. But for this gas to collapse and form the first stars, it faced a critical problem. It needed to cool down. As gas collapses under gravity, it heats up, and this increased pressure can fight back against further collapse. In our modern universe, gas clouds cool efficiently by radiating away their heat through heavy elements like carbon and oxygen. But in the pristine universe of the Dark Ages, these elements did not yet exist. The gas was pure, composed only of hydrogen and helium, which are very poor radiators. How could this pristine gas possibly cool enough to form the first structures? The answer lies in a fragile and simple molecule, molecular hydrogen, or H2. This molecule, just two hydrogen atoms bound together, became the universe's first and only cooling system. Its formation was a slow and delicate process. It began when two neutral hydrogen atoms collided. One would occasionally kick its electron into a higher energy state, and as it fell back down, it would release a tiny amount of energy in the form of a faint infrared photon that could escape the cloud. This process allowed the gas to shed just enough gravitational energy to continue its slow-motion collapse into the waiting gravitational wells of the dark matter halos. This molecular hydrogen cooling was incredibly inefficient compared to the metal line cooling we see today, but it was just enough to tip the balance. Deep within the darkest, densest pockets of the early universe, the first protogalactic clouds began to cool, fragment, and condense, setting the stage for the gravitational collapse that would ignite the very first stars and end the Dark Ages forever. The tantalizing possibility for modern astronomers is that this entire epoch might not be completely lost to time. The neutral hydrogen gas that filled the dark ages was subtly interacting with the background radiation field, and it should have emitted a very specific radio signal at a wavelength of 21 centimeters, just as it did later during reionization. But this signal is from a much earlier time, and the expansion of the universe has stretched this faint whisper to monumental proportions. The signal from the heart of the Dark Ages, when the first structures were just beginning to coalesce, is now redshifted to wavelengths of several meters, placing it in the long-wave radio band. Detecting this signal would be the ultimate time machine, offering a direct glimpse into the universe before any stars existed. The potential reward is nothing less than a dynamic map of the cosmos in its infancy. By tuning a radio telescope across different meter-long wavelengths, astronomers could, in theory, slice the Dark Ages into different cosmic times. They could watch the gravitational growth of the very first structures in real time, seeing how the dark matter scaffolding pulled the gas into the first filaments and halos. They could pinpoint the exact moment and location where the first molecular hydrogen began to form and cool, and perhaps even identify the sites where the very first population 3 stars were destined to be born. This signal would bridge the gap between the pristine simplicity of the cosmic microwave background and the complex, ionized universe that followed, revealing the entire story of how our structured cosmos emerged from a near-perfect smoothness. However, the technical challenges involved in this detection are quite literally astronomical. The signal is unimaginably faint, buried under a roar of foreground radio interference that is millions of times stronger. This interference comes from our own galaxy's synchrotron radiation, the collective radio buzz from all the distant galaxies in the universe, and perhaps most frustratingly, from human-made radio frequency pollution on Earth. Extracting the cosmic signal would require not just an incredibly sensitive radio telescope, but one located in a perfectly radio-quiet environment like the far side of the Moon. Projects are already being dreamed up for lunar orbit or the lunar surface, where the Moon's bulk would act as a natural shield against the radio noise of Earth. The hunt for the Dark Ages signal represents the next great frontier in observational cosmology, a quest to witness the very beginning of structure formation and hear the faint echo of the universe waiting in the dark. While we often picture the early universe in terms of light, gravity, and raw energy, there may have been another invisible force subtly shaping the entire reionization process: magnetism. This brings us to a truly frontier mystery, one that pushes the boundaries of both theory and observation. Did primordial magnetic fields, woven into the fabric of the cosmos and amplified by its first violent events, play a hidden but crucial role in lighting up the universe? The very origin of cosmic magnetic fields is a profound puzzle. One possibility is that they are truly primordial, generated by exotic physics in the instants after the Big Bang, perhaps during a phase of rapid inflation. These seed fields would have been unimaginably weak, a faint imprint on the newborn cosmos. Alternatively, they could have been forged later through astrophysical processes, created in the turbulent shocks of the first supernova explosions, or by powerful dynamos in the accretion disks of the first black holes. Regardless of their origin, once established, even a weak magnetic field could have been dramatically amplified by the churning motions of gas collapsing into the first galaxies and halos. As gravity pulled gas inward, any tiny magnetic field lines would have been dragged along, compressed, and wound up, strengthening the field in a powerful feedback loop. So how could these amplified fields have influenced reionization? Their impact would have been multifaceted, acting on both the sources of ionizing radiation and the medium through which it traveled. First, consider the formation of the first stars themselves. Magnetic fields introduce pressure and tension, which can resist the gravitational collapse of a gas cloud. In some cases, this could have slowed down star formation, preventing gas from fragmenting as efficiently and potentially leading to the creation of even more massive population 3 stars. A more massive star burns hotter and brighter, producing a far greater flux of ionizing photons throughout its short life. In this way, magnetic fields might have indirectly boosted the ionizing output of the very first stellar generations. Second, magnetic fields are master architects of chaos and structure. When the first massive stars inevitably died in supernova, their explosive shock waves would have propagated out into the surrounding gas. Magnetic fields threading through this gas would have channeled these shocks, guiding their energy and influencing how they interacted with the interstellar medium. Instead of a uniform, spherical blast wave, the explosion would have been funneled along magnetic field lines, potentially carving out long, narrow chimneys and cavities through the dense gas of a primordial galaxy. These magnetically guided pathways could have served as perfect escape routes for ionizing photons, effectively increasing the critical escape fraction. A galaxy with a strong, organized magnetic field might have been a far more efficient leaky lighthouse than one without, its hard radiation shooting out along these magnetic highways to do its work on the intergalactic medium. Beyond the galaxies, magnetic fields could have also influenced the vast intergalactic medium itself. The same fields that helped photons escape might have also helped structure the cosmic fog they were trying to clear. Magnetic pressure could have provided additional support to dense clouds of neutral hydrogen, making them more resilient against ionization, and perhaps explaining why some pockets of gas held out as the last neutral frontiers for so long. Furthermore, as the first ionized bubbles expanded, they would have carried their magnetic fields with them into the voids, potentially magnetizing the entire universe in the process. The magnetic fields we measure in galaxy clusters and the intergalactic medium today might be the fossil remnants of this very amplification and dispersal during the reionization era. The challenge, of course, is that observing magnetic fields at such incredible distances is currently beyond our technical capabilities. We cannot directly image the magnetic fields around a galaxy 13 billion light-years away. However, the next generation of observatories offers hope. The square-kilometer array, with its unparalleled sensitivity to radio waves, may be able to detect the faint signatures of magnetic fields in the most distant galaxies we can find. It could look for the telltale polarization of radio light that indicates the presence and orientation of magnetic fields. Additionally, by studying the strength and distribution of magnetic fields in nearby galaxies that are analogs of the first systems, we can build better models to extrapolate back in time. While still speculative, the potential influence of magnetism adds a fascinating and complex layer to the story of reionization, reminding us that the universe's transition from darkness to light was likely orchestrated by a symphony of forces, both seen and unseen. But the story of helium's ionization may be even more complex and dramatic than a single, late-breaking event. This brings us to a fascinating and controversial idea known as the double reionization hypothesis. What if the universe didn't ionize helium just once, but actually did it twice? This theory proposes a cosmic cycle of illumination and darkness for this ancient element. A first, early attempt that ultimately failed, followed by a much later and final success. To understand how this could even be possible, we need to revisit the unique challenge of ionizing helium. Stripping both electrons from a helium atom requires photons of truly extreme ultraviolet radiation, each carrying more than 54 electron volts of energy. For a long time, astronomers assumed only one type of object in the young universe could produce such a ferocious flux of these hard photons: quasars powered by supermassive black holes. And since quasars took time to form and reach their peak numbers, this neatly explained why helium reionization happened billions of years after hydrogen reionization. However, the double reionization hypothesis suggests there might have been an earlier, temporary chapter written by a different cast of characters, the legendary population 3 stars. These first stellar titans, born from perfectly pristine gas, were not just massive, they were incredibly hot. Their surfaces blazed at temperatures that could reach 100,000 degrees Kelvin, far hotter than most stars today. Such extreme heat means their radiation would have been shifted toward the high-energy end of the spectrum, producing a significant amount of the very photons needed to ionize helium. If these stars formed in sufficient numbers, they could have potentially created localized bubbles where not only hydrogen was ionized, but helium was too. For a brief, brilliant period, helium reionization might have begun in earnest right alongside hydrogen, but this first attempt was likely doomed from the start. The same property that made population 3 stars so powerful, their tremendous mass also made their lives tragically short. They burned through their nuclear fuel in just a few million years before exploding as hypernova. When they died, the intense source of their hard radiation vanished instantly. In the regions they had cleared, the ionized helium atoms would have quickly started to recapture free electrons, a process known as recombination. Without a steady, sustained source of new hard photons to maintain the ionization, the helium would have slipped back into its neutral state. The first reionization of helium would have been a fleeting cosmic event, a false dawn that flickered out almost as quickly as it began, leaving the helium once again shrouded in neutrality until the quasars later arrived to finish the job for good. The evidence for this tantalizing scenario is indirect and hotly debated. The most compelling clues come, once again, from the intricate patterns of the Lyman alpha forest in quasar spectra. Some observations show puzzling variations in the ionization state of helium in different regions of space at the same cosmic time, which could be echoes of an earlier, patchier ionization event. Furthermore, the temperature of the intergalactic gas at these early epochs might be slightly higher than some models predict, which could be the residual heat left over from a first, violent wave of ionization by incredibly hot stars. However, the case against double reionization is also strong. The biggest hurdle is the sheer number of population 3 stars required. Could they have ever been numerous enough to produce a universe-wide effect, even a temporary one? Many simulations suggest that while these stars were powerful, they were also too rare and short-lived to coordinate a large-scale helium reionization. Their individual bubbles would have been small and isolated, and their collective impact may have been little more than a few bright flashes in the vast dark, unable to truly kick-start a global process that would only later be completed by the rising power of quasars. Ultimately, the double reionization hypothesis forces us to ask a deeper question about the early universe: just how efficient were its first engines? Whether this theory is confirmed or refuted, it pushes our models to their limits and refines our search for answers. It challenges us to look for even subtler fingerprints in the light from the edge of time, seeking evidence of a forgotten first attempt to illuminate the cosmos fully, a brilliant but failed effort that preceded the final, lasting victory of light over darkness. But while stars and quasars dominate our picture of cosmic reionization, there may have been another, more subtle class of engine at work, hidden within the hearts of those first galaxies. This brings us to a compelling and often overlooked mystery: the potential role of X-ray binaries. Imagine not a brilliant star or a dazzling quasar, but a dark, compact object locked in a deadly gravitational dance with a companion star. A neutron star or a stellar mass black hole, spinning fiercely as it pulls a stream of gas from its neighbor. As this stolen matter spirals inward at nearly the speed of light, it is compressed and heated to millions of degrees, unleashing a torrent of high-energy X-ray radiation. These systems are not merely cosmic curiosities. They are incredibly efficient and penetrating sources of power that could have played a unique and crucial part in preparing the universe for its great transformation. The ionizing power of an X-ray binary operates on a different principle than the ultraviolet light from stars. A UV photon is perfectly tuned to rip apart a hydrogen atom in a single, direct hit. An X-ray photon, however, carries hundreds or even thousands of times more energy. When it slams into an atom, it doesn't just liberate an electron, it creates a cascade of destruction. The initial impact can kick out a deeply bound electron with tremendous force, and that high-energy electron then goes on to collide with other atoms, ionizing them in turn. This creates a chain reaction, a shower of secondary ionizations that allows a single X-ray photon to ionize many hundreds of hydrogen atoms. While less efficient on a per-photon basis than direct UV light, the penetrating power of X-rays is their greatest asset. UV photons are easily absorbed by even small amounts of neutral hydrogen, which is why the first starlight was initially trapped in small bubbles. X-rays, by contrast, can travel vast distances through a neutral medium before being absorbed. They could have pierced deep into the cosmic fog, pre-ionizing and preheating large regions of gas long before the UV fronts from stars and quasars ever arrived. This leads to a fascinating possibility that X-ray binaries may have contributed to a more extended and uniform reionization process. Instead of the sharp, aggressive ionization fronts from UV sources, X-rays would have created a widespread, diffuse background of softer ionization. They would have gently heated the gas, raising its temperature and pressure and making it more resistant to gravitational collapse. This preheating could have had a regulatory effect on the formation of the very first stars and galaxies, potentially suppressing the birth of the smallest systems and slightly delaying the overall process. In this view, reionization wasn't a sudden explosion of light, but a gradual warming, a cosmic spring that thawed the universe slowly from the inside out, with X-ray binaries acting as a distributed network of underground heaters. The critical question, then, is whether these systems were common enough in the early universe to make a difference. There is strong reason to believe they were. The first generations of stars were overwhelmingly massive, and massive stars die quickly, leaving behind neutron stars and black holes. In the dense, chaotic environments of primordial galaxies, it's highly likely that many of these remnants would have found themselves bound in binary systems with another star, readily available to begin their accretion feast. The low metallicity, the lack of heavy elements in these early galaxies might have actually favored the formation of more massive black hole remnants, leading to even more powerful X-ray binaries. We see evidence of this in nearby galaxies that are poor in metals. They often host what are known as ultra-luminous X-ray sources, objects far brighter than typical X-ray binaries in our own Milky Way. If the early universe was teeming with such objects, their collective X-ray output could have created a pervasive background radiation field that subtly but significantly influenced the entire reionization timeline and topology. Ultimately, the contribution of X-ray binaries reminds us that the story of cosmic reionization is not a simple tale with a single hero. It was likely a complex interplay of many different sources, each with its own unique signature. The brilliant UV flash of massive stars, the piercing beams from quasars, and the deep, penetrating glow of X-ray binaries all worked in concert, each playing a different part in the orchestra of ionization. The hard UV radiation might have provided the final, decisive push to clear the gas, but the X-rays may have done the crucial preparatory work, softening up the target and ensuring that the universe became not just ionized, but ionized in a particular way. Unraveling their specific role requires looking for their faint fossil imprint in the temperature and ionization state of the most ancient gas we can observe, a subtle clue hidden within the light of the first quasars that points to a deeper, more intricate dawn. To truly rate the history of the universe's transformation, we must learn to interpret its most complex and beautiful fossil record, a natural archive written in light itself. This brings us to one of the most powerful tools in all of cosmology, a celestial barcode that contains a wealth of information about the cosmic web, the Lyman Alpha Forest. When we point our most powerful telescopes at a distant quasar, we aren't just measuring its brilliance, we are dissecting its light, and in doing so, we are reading a detailed diary of every cloud of hydrogen gas its light has passed through on its billion-year journey to Earth. The result is a quasar spectrum that is anything but a smooth curve. Instead, it is carved up by a dense, intricate thicket of absorption lines, a veritable forest of dips and troughs. Each one of these lines is the fingerprint of a specific cloud of neutral hydrogen at a specific distance, and together they form a one-dimensional map of the cosmic web along that single, razor-thin line of sight. The story this forest tells is one of profound change. As we look at quasars at different distances, and therefore at different redshifts, we can watch the evolution of the intergalactic medium unfold. In the spectra of the most distant quasars, those whose light began its journey before reionization was complete, we see something dramatic, a Gunn-Peterson trough. This isn't a forest, it's a barren plain. It signifies that the light has passed through a vast, continuous sea of neutral hydrogen that absorbed all the light at that specific wavelength, leaving a stark, silent gap in the spectrum. But as we look at quasars that are closer to us, corresponding to times after reionization, the forest appears. The once opaque universe has become a misty realm filled with countless discrete clouds of neutral gas, each one creating a single, narrow absorption line. The very existence of this forest is direct proof that reionization happened. The smooth, neutral blanket has been shattered into a mist of clouds suspended within a hot, ionized plasma. But the forest does more than just confirm the event. It chronicles its aftermath with exquisite detail. The density and properties of these absorbing clouds change over cosmic time, acting as a precise barometer for the intensity of the ionizing background radiation. After reionization, the universe is filled with a diffuse, pervasive glow of ultraviolet light from all the galaxies and quasars. This radiation bathes every hydrogen cloud, constantly trying to rip it apart. The survival of any cloud is a delicate balancing act between gravity, which tries to hold the cloud together, and the external radiation field, which tries to evaporate it. By studying the forest, we can measure this balance. A stronger, more intense ionizing background will efficiently evaporate the smaller, denser clouds, causing them to vanish. This leads to a gradual thinning of the Lyman alpha forest over billions of years. The number of absorption lines decreases, and the lines that remain are predominantly from the largest, most massive clouds that have enough gravitational strength to withstand the relentless external radiation. The evolution of the forest is therefore a direct measurement of the growing power of the universe's total light output after the lights first came on. This brings us to the sudden and mysterious change observed at a redshift of around 6, a point where the universe was roughly 1 billion years old. When astronomers study quasars just beyond this distance, the forest looks fundamentally different. The absorption lines are so numerous and so deep that they blend together, creating what's known as a Lyman alpha swamp. It's a region of the spectrum that is almost completely black due to the absorption from a very high density of neutral hydrogen. Then, quite abruptly, at redshifts lower than 6, the familiar, thinner forest reappears. This sudden transition is widely interpreted as the final, tail end of the reionization process. It marks the epoch when the very last major pockets of neutral hydrogen in the intergalactic medium were finally evaporated and ionized, making the universe truly transparent all the way through. However, the story is not so simple. This transition is not sharp and uniform, it's fuzzy and occurs over a range of redshifts, and it appears to happen slightly differently along different lines of sight. This is the critical clue that reveals the profound inhomogeneity of reionization. The universe did not clear up everywhere at once. Some lines of sight, perhaps those pointing through an overdense region that was ionized later, will show a swampy, saturated forest at a redshift where another line of sight, looking through a vast void that was cleared early, already shows a well-developed, thinner forest. This patchiness is the lingering echo of the bubble-like nature of the process. The sudden change at Z tilde 6 isn't a universal switch being flipped. It is the final merging of the last few stubborn bubbles, the point at which the ionized regions finally overlap to such a degree that no line of sight could any longer travel through a significantly large neutral patch. The Lyman alpha forest is therefore more than a fossil. It is a dynamic record that captures both the completion of reionization and the complex, clumpy journey it took to get there, preserving the memory of a universe lighting up one neighborhood at a time. But for all the breathtaking imagery provided by the James Webb Space Telescope, a picture can only tell us so much. To truly confirm the distance of these ancient galaxies and to understand the physical conditions within them, we need more than just a pretty picture. We need to dissect their light. This brings us to our 23rd mystery, a high-stakes scientific race to perform a feat of cosmic spectroscopy, to capture the faint spectral fingerprint of the most distant objects in the universe and use it to map the final stages of the reionization era itself. When astronomers point Webb's powerful spectrographs at a candidate galaxy from the cosmic dawn, they are not just measuring its brightness, they are spreading its light out into a rainbow of wavelengths, creating a unique barcode that holds the secrets to its composition, temperature, motion, and most importantly, its redshift, a direct measure of its distance due to the expansion of universe. The most sought-after feature in this barcode is a specific emission line known as Lyman alpha. It's a bright spike in the spectrum caused when an electron within a hydrogen atom falls from a higher energy level to the lowest one, releasing a photon with a very specific wavelength of 121.6 nanometers. In a laboratory, that's in the far ultraviolet. But for a galaxy at a high redshift, the expansion of the universe stretches this wavelength into the infrared, right into the sweet spot of Webb's instruments. Detecting this line is the gold standard for confirming a galaxy's distance. It's a clean, unmistakable signal that screams, "I am here at this specific point in cosmic history." However, the journey of a Lyman alpha photon is a perilous one, and its fate is directly tied to the ionization state of the universe. In a fully neutral universe, like the one that existed before reionization, space is filled with a dense fog of hydrogen atoms. A Lyman alpha photon emitted by a young galaxy doesn't get far. It is almost immediately absorbed by a nearby neutral hydrogen atom, only to be re-emitted a moment later in a random direction. This process of absorption and re-emission, known as resonant scattering, happens over and over again. The photon effectively performs a random walk, bouncing endlessly through the fog, its path lengthened by millions of light years. With each scattering, there's a high chance it will be eventually absorbed for good or simply never reach our telescopes. The result is that in a predominantly neutral medium, the brilliant Lyman alpha emission from a galaxy is suppressed, scattered, and effectively hidden from our view. This scattering property transforms Lyman alpha from a simple distance marker into a powerful probe of the reionization process. The key is to look at a large sample of galaxies at a given redshift and ask a simple question: what fraction of them show strong Lyman alpha emission in their spectra? This is known as the Lyman alpha fraction. If the universe at that time is still largely neutral, the fraction will be very low. The fog is too thick for the signal to get through. But as reionization progresses and the ionized bubbles grow and merge, clear pathways open up. Photons emitted from galaxies inside these large, transparent bubbles can travel much farther without being scattered. When the bubble around a galaxy becomes sufficiently large, the Lyman alpha photons can escape their local environment and stream across the universe to be captured by our telescopes. Therefore, an observed increase in the Lyman alpha fraction at a specific redshift is a direct indicator that the universe was becoming significantly more transparent at that epoch. It's like watching the fog lift in real cosmic time. This creates a fascinating and complex puzzle. Webb is now finding galaxies at redshifts above 7, a time when the universe was still thought to be partially neutral. Intriguingly, some of these galaxies show strong Lyman alpha emission, while others, at the very same distance, do not. Why this difference? The answer likely lies in the patchy, bubble-like nature of reionization. A galaxy that shows the line probably resides in a large, fully ionized bubble. Its light granted a clear exit. Its neighbor that lacks the line might be trapped in a smaller bubble or even just outside one, its signal still stifled by the surrounding neutral fog. This isn't a contradiction, it's a confirmation of the inhomogeneous model. The presence or absence of the line in individual galaxies is telling us about their immediate surroundings, allowing us to map the geometry of the ionized regions. By measuring the Lyman alpha fraction across different regions of the sky and at different redshifts, astronomers can literally chart the progress of reionization in 3 dimensions, watching as the fraction steadily increases over time, marking the triumphant retreat of the cosmic darkness and the final victory of light. Yet for all the incredible progress we've made, the story of cosmic reionization remains unfinished, a tapestry with many threads still waiting to be woven into place. The answers to the 24 mysteries we've explored won't be found in our current data alone. They lie in the future, in the light yet to be captured by a new generation of observatories that will push the boundaries of what we can see. We are on the cusp of a revolutionary era in cosmology, where these powerful new eyes on the sky will work in concert to provide our first complete, multi-wavelength portrait of the universe's transformation from darkness to light. Leading this charge is the James Webb Space Telescope, an instrument that has already begun to rewrite the textbooks. Its profound infrared sensitivity allows it to do what was once thought impossible: directly detect and characterize the faint, whispering glow of the very first galaxies. Webb isn't just finding a handful of bright outliers, it is conducting a deep and thorough census of the early universe, revealing a teeming population of small, faint dwarf galaxies that were previously entirely invisible. By analyzing the spectra of these ancient systems, astronomers can measure their distances with precision, determine their chemical compositions, estimate the ages and temperatures of their stars, and crucially, calculate their production of ionizing photons. Webb is moving us from speculation to solid statistics, allowing us to finally answer the fundamental question: were there enough galaxies to provide the photon budget needed for reionization? Every new deep field image brings us closer to a definitive answer. But while Webb excels at ultra-deep, narrow-field observations, it cannot easily find the rarest, most brilliant objects in the vast expanse of the early universe. This is where the Nancy Grace Roman Space Telescope will play its pivotal role. Scheduled for launch later this decade, Roman is designed not for depth in a tiny patch of sky, but for incredible breadth. Its field of view is over 100 times larger than Hubble's infrared camera. This allows it to perform wide-field surveys of unprecedented scale, scanning enormous volumes of the cosmos to find those exceedingly rare, luminous beacons, the most distant quasars and the brightest, most massive galaxies from the reionization era. Finding these objects is like finding needles in a cosmic haystack, but they are crucial needles. They represent the most powerful engines of ionization, and by counting their numbers and mapping their distribution, Roman will tell us whether these monsters were common enough to play a dominant role, or if they were simply spectacular exceptions to the rule of faint, numerous galaxies. Together, Webb and Roman will provide the complete picture of the sources, from the countless faint dwarfs to the rare brilliant giants. However, even these magnificent optical and infrared telescopes can only show us the light sources themselves. They cannot directly show us the cosmic fog that was being cleared. To witness the actual process of reionization unfolding, to see the bubbles of ionized plasma growing and merging in real cosmic time, we must turn to a different window on the universe, the radio spectrum. This is the mission of the Square Kilometre Array, or SCAR, a revolutionary observatory currently under construction across radio-quiet deserts in South Africa and Australia. The SKA will consist of thousands of radio antennas working in unison to achieve a collective collecting area of, as the name implies, a square kilometer. Its primary goal is to detect the faint 21 centimeter signal from neutral hydrogen at the highest redshifts. Unlike Webb and Roman, which take snapshots of individual galaxies, the SKA will make a dynamic movie. By tuning its antennas to different frequencies, it will slice the early universe into thin cosmic time slices. In each slice, it will map the fluctuations in the 21 centimeter signal, revealing the precise geometry of the ionized bubbles and the remaining neutral patches. The statistics of these bubbles, their sizes, shapes, and how they cluster, will be a direct fingerprint of the sources that created them, finally revealing whether reionization was driven by many small galaxies or a few powerful quasars. The true power of this new era lies not in any single observatory, but in their synergy. This is multi-messenger astronomy on a cosmic scale. Webb will find the galaxies and tell us how many ionizing photons they were producing. Roman will find the rare, bright quasars and massive galaxies that Webb might miss in its deep but narrow fields. And the SKA will show us the direct impact of all that radiation on the intergalactic medium, mapping the resulting bubbles. By combining these datasets, we will be able to directly connect cause and effect. We will see, for example, how a cluster of galaxies found by Webb and Roman correlates with a large ionized bubble mapped by the SKA. This multi-wavelength approach will transform reionization from a set of competing theories into a detailed, observational science with a clear timeline and a known cast of characters. These observatories represent our greatest hope for turning the profound mysteries of the cosmic dawn into a settled understanding, finally revealing the complete story of how our universe emerged from the darkness to become the brilliant, transparent expanse we call home. Yet this grand narrative of cosmic evolution leads us to a final, deeply human mystery, one that transcends the physics of ionization and the statistics of galaxy formation to touch on something far more profound, our own place in this story. The reionization era was not merely a physical transition, it was the pivotal chapter that set the stage for everything that followed, including us. Every element essential to life as we know it, the carbon in our cells, the oxygen we breathe, the iron in our blood, was forged in the fiery hearts of those first stars and scattered across the cosmos in their cataclysmic deaths. The supernova explosions that ended the brief lives of the population 3 stars were not just conclusions, they were the necessary dispersals that seeded the pristine universe with the first heavy elements. This enrichment process transformed the cosmos from a simple soup of hydrogen and helium into a complex chemical laboratory, providing the raw materials for future generations of stars, rocky planets, and ultimately, biological organisms. We are quite literally the children of those first stellar generations, our very atoms a legacy of that primordial alchemy. This realization completes a breathtaking cosmic cycle. The same light that began the process of ionization over 13 billion years ago, the radiation that first pierced the darkness and gradually cleared the fog to create a transparent universe, is now allowing us to see back to our own origins. Our most powerful telescopes are time machines collecting photons that have traveled since the dawn of time. When the James Webb Space Telescope stares into the abyss, it isn't just collecting data. It is gathering the ancient light that helped make the universe habitable and using it to understand the very conditions that allowed for its own creation and ours. We are the universe awakening to itself, using the tools and the clarity it provided to trace its own history. This act of observation is a profound closing of the loop. The universe became transparent, which allowed structures to form, which led to planets and life and intelligent beings who could build instruments to look back and ask how it all happened. The philosophical implications are staggering. The reionization era underscores our profound connection to the cosmos. We are not separate observers looking into an external universe. We are a product of its most fundamental processes, an emergent property of its evolution from simplicity to complexity. Understanding this era is therefore an act of self-discovery. It answers the most fundamental questions about our origins, where the materials that constitute us came from, how the environment that allows us to exist was created, and why the universe is structured in a way that is ultimately knowable to us. The story of cosmic reionization is, in its deepest sense, the first chapter of our own story. It tells us that the conditions for life were not a late addition, but were written into the laws of physics from the very beginning, set into motion by the first sparks of light in the cosmic dark. Our quest to understand it is the universe reflecting upon its own beginnings, a testament to the beautiful and mysterious fact that we are a way for the cosmos to know itself. And so our journey through the 25 great mysteries of the Cosmic Reionization Era brings us full circle, from the first flickers of starlight to the final, fading whispers of neutral gas. We've navigated the profound questions surrounding the universe's most dramatic transformation, exploring the titanic first stars, the swarms of faint galaxies, the ferocious quasars, and the invisible hand of dark matter that orchestrated it all. Each mystery we've touched, from the elusive escape fraction to the patchy bubbles of ionization, from the fossil heat in the intergalactic medium to the potential influence of magnetic fields, is not an isolated puzzle. They are all deeply interconnected threads in a single, magnificent tapestry, each one vital to understanding the whole. The timeline of reionization is shaped by the nature of its sources. The topology of the bubbles points to their power and clustering. The lingering heat tells us about the hardness of the radiation that did the work. This era was not a simple event, but a complex, dynamic, and chaotic symphony of physics playing out across hundreds of millions of years. Reflecting on how far we've come is truly humbling. Just a few decades ago, the reionization era was a purely theoretical chapter in our cosmic history, a necessary but unobserved bridge between the afterglow of the Big Bang and the universe of galaxies we see today. Now it is a vibrant field of observational science. We have moved from speculation to evidence, from ideas to data. The cosmic microwave background has given us a global timeline. The spectra of distant quasars have revealed the Gunn-Peterson Trough and the Lyman Alpha Forest. And now, the James Webb Space Telescope is delivering a stunning census of the galaxies that likely powered the entire process. We have real constraints, real measurements, and a framework that, while still incomplete, is being tested and refined with every new observation. Yet for every answer we find, new and deeper questions emerge. The initial photon budget shortfall appears to be closing as we find more and more faint galaxies, but the exact escape fraction remains maddeningly elusive. We are building a movie of the cosmic dawn, but many of the frames are still missing or blurred. This is not an end, but a magnificent beginning. The next decade promises to be the most revolutionary period in the history of cosmology. The James Webb Space Telescope will continue its deep surveys. The Nancy Grace Roman Space Telescope will map vast volumes of the early universe, and the Square Kilometre Array will, for the first time, attempt to directly map the neutral hydrogen itself, giving us a three-dimensional view of the reionization process as it happened. These observatories, working in concert, will transform our understanding from a collection of compelling theories into a detailed, observational history. They will likely Chinese letter some of our most cherished assumptions and reveal surprises we cannot yet even imagine. The story of the cosmic dawn is still being written, and we are privileged to live in the time when its most crucial pages are being turned. So I encourage you to stay curious, to follow along with every new discovery and every new image from the edge of time. The greatest mysteries of the universe's youth are waiting to be solved, and we all have a front row seat to watch them unfold.